So, functions. What are they? What do they do for us? So that's kind of a heady topic, but in truth, calculus really is kind of all about this idea of what we call a function at heart. If you go far enough into mathematics, eventually this branch of study just ends up kind of getting called function theory, if that gives you any idea. So it can be a really broad, encompassing notion. So the basic idea is the following. You kind of have a couple of sets. For our purposes, they're generally numbers, but they could be any kind of objects. And you got some, dots over here that aren't showing up because I didn't make them big enough. Here we go. That's a little better. Then we got some dots over here. And what a function is, it's kind of like a map. It tells us how to get from a particular dot over here to a corresponding dot over on this side. So you can think of a function which we really normally represent with a letter like f, g, that kind of thing. So you'll have some value y living over here that is a function of x. So that's not representing like a multiplication or anything. That's not f times x. It's f of x. So, and technically we're going to have a whole bunch of these little arrows as we go from values over here, what we would call the domain of our function, this set on the left. The values over here on the right, we would call the range of our function. So that's just kind of a picture to give you the idea as to what's going on. So most of the time, we're not going to be dealing with functions at this abstract level, where we're just talking about generic sets and ways to connect dots between the two sets or anything like that. Or functions that we're going to talk about come at us in 3 flavors essentially. You could see a function that comes to us via a graph, like a geometric representation. So you've got, like a graph of a function, like your calculator or generator or whatever. You could also have a function that comes at you as a table of values. If you're in the sciences, that's how you end up getting most of your functions in the first place, because you're probably measuring something in a laboratory setting, and that's where your functions are arising. You've got pairs of numbers that are lined up. For a lot of what we're going to be doing in calculus, we tend to assume that the function is coming to us via a formula of some sort of like what we've already been dealing with. So let's play around with a formula real quick. I wasn't kidding when I say I get maximum mileage out of my examples. So you recall this from our last video where we had y equals this thing. Again, you'll often think of sort of that y coordinate as being like the value of the function. So the y and the f of x are often interchangeable in this sense. Anyway, so if we were wanting to evaluate this function for a given x value, so for instance, if I wanted f of 1, then everywhere I see an x in this expression, I plug in the number 1. So I'd have 2 times 1 squared, minus 12 times 1, minus 14. Again, make my multiplication dots a little more clear. And you work through the arithmetic in this instance. It's not too tough to work out. Minus 12 minus 14 is negative 26. So yeah, we get, what, negative 24 out of that. So by the same token, if I wanted f of negative 1, again, everywhere I see an x in my formula, the negative 1 goes in its place. So we have 2 times negative 1 squared minus 12 times negative 1 minus 14. And this ends up changing things up. And as you may recall when we were talking about the graphical qualities related to this equation, yeah, if I work out the arithmetic here, I get 0 because negative 1 was one of our function's x-intercepts. So there's that. Now, so plugging in numbers is pretty straightforward. If there's any pitfall I would mention, do recall, be careful when you're plugging like negative numbers in there. Yeah, make sure you're enclosing things in parentheses appropriately. Now, maybe a bit more of a stretch would be, well, what happens if we see something like that? So f of x plus 1. Now, in this instance, Everywhere we see an x, what's going to go in its place? The thing in the parentheses, just like we had the 1 before, and then the minus 1. Now everywhere we see an x, x plus 1 goes into that slot. And I'm creeping over to where I've got to kind of like stand myself in the corner. So yeah, everywhere we see an x in the original formula, now we've got an x plus 1 there. Now we need to work through, the algebra because it's kind of clunky to leave it like this, right? So I'm going to leave it to you to check via the FOIL algorithm or whatever your favorite approach for working out what x plus 1 quantity squared is going to be. You should get this guy right here, x squared plus 2x plus 1. Distribute the negative 12 across there. So I should have gone ahead and distributed the 2 at this point, but yeah, you could take care of that. 2x squared plus 4x plus 2, right? So distribute the negative 12. Negative 14 is still just kind of hanging around in the back. So when it's all said and done, we get 2x squared, 4x minus 8x, because this gives us a plus 4x, minus this 12x right here. So minus 8x, then we have plus 2, minus 12 would give me negative 10, minus 14, negative 24. Now, if you were so inclined, you could start doing some, trying some algebraic shenanigans to, factor this thing out, but that's not necessary for our purposes here. So that's what we would get if we replace all of our x's with x plus 1s. And that's kind of a meaningful question, like as to how would things be different if I just wrote f of x plus 1. So you can hopefully see all that would really do is we take this guy right here. That's our formula for f of x. Given an x value, that's what it tells us. We take that and we just kind of slap a plus 1 on the back. And you can work through that and then compare and see, well, does that formula end up giving me the same thing that I would get out of what I just did right here? That's a question I'm going to leave to you for now. So that's an example of a function. They said, well, we'll see plenty of these by the time the semester's over. We'll talk about what we want to call a polynomial function like this. This is a quadratic polynomial function. You can have more involved polynomials. You could have an exponential function where instead of having 2x squared, you have like the 2 is the base and the variable x is living up in the exponent. Or our friends, the trigonometric functions. We talk about sines and cosines and tangents and that sort of thing. So there was one more example I wanted to take a look at real quick here, so bear with me. So having single functions works well. It does an awful lot of stuff for us, but every now and again we'll have multiple functions that we need to put together in some way, shape, or form. So you have sort of your standard arithmetic combinations of functions. You could take two functions and add them together. You add the formulas together. You could multiply them and then multiply. Maybe you need to FOIL or something like that. You could divide, so you have one function living over top of another one, that kind of thing. The trickiest of those operations that you might need to deal with is what we would call composing functions. And it's kind of, the idea is you iterate the functions on each other. Like you do one and then do the other with the result. So, for instance, you may have seen in the past this represented with like a little bubble of g of x, so it looks like fog of x. These mean the same thing. Functionally, I like kind of writing it like this. So the idea here is if you follow like your order of operations, parentheses come first, you got to deal with g of x because it's on the inside, and then we do f, whatever f tells us to do, on what comes after that. So you can kind of imagine f of g of x in this case. We take f of, and you can just fill in this formula, f of 1 over x, and now, just like we saw with that quadratic example, anywhere an x appears in this formula right here, we put this guy in its place. So we get the square root of 1 over x plus 1. So And the thing I wanted to point out here is that composition, unlike, say, like addition or multiplication, those operations are what math teachers have always called commutative. Like 2 times 3 and 3 times 2, they mean the same thing, right? You get 6 either way. Function composition, yeah, not so much. So if we flip the order here, the way this is written, parentheses, again, they say we do f of x first, and then we perform whatever g tells us to do on that. So we would have g of square root of x plus 1, and now we take this guy and we feed him into the formula we have for g of x, which is going to look like that. 1 over the quantity square root of, x plus 1. And I don't want you to get too deep into it, but you'll probably be willing to take my word for it. These two things, they're not algebraically equivalent to each other. Please don't try to convince yourself those two are the same thing. They're not. As I said, function composition doesn't commute, so the order in which these guys are written really does make a difference here. So again, hopefully this is not new territory. You've talked about functions and more involved, as you see, you can get a lot deeper into things like domains and ranges and so on and so forth. But in terms of just getting things introduced to get us back up to speed on the the really key pieces we need for calculus, I think this will do the job for us. So that's it for now. Got another video coming up with a little more preamble type material.